Our universe is composed of billions of galaxies, so interactions between them are inevitable. One potential interaction is a galaxy merger, which may occur when galaxies become close enough to exert gravitational forces on each other. This is supported by observational evidence of merging galaxies. Galaxy mergers are some of the more significant interactions that we study due to the massive amounts of interacting components. Let's examine what happens to baryonic matter during a galaxy merger. Now, as a reminder, baryonic matter refers to the gas, dust, and stars in a galaxy. The first observable sign of an interaction is a tendril of gas and dust reaching out between the two galaxies. This tendril of gas and dust is called a tidal tail. As the cores of both galaxies eventually unite, the orbits of stars become disrupted, and the galaxies may even move through each other multiple times before settling into a new configuration. Through this process, much of the original shape and organization of baryonic components is reconfigured. There are different ways galaxy mergers can be classified, and we will explain two. A minor merger refers to a merging where one of the galaxies is significantly larger than the other, and these types of mergers are thought to be the ones that form galaxies like spirals. On the other hand, a major merger refers to the merging of two galaxies of comparable mass, such as when two spiral galaxies merge to form an elliptical galaxy, a merger thought to be the main source of elliptical galaxy formation. So what is the purpose of looking at these behemoths in our universe? According to Hubble's 2008 review, astronomers estimate that 1 in 20 disk or spiral galaxies are in the process of colliding. Observations and simulations support the notion that spiral galaxies are formed through a series of minor mergers. So, understanding more about a galaxy merging as a whole will provide information about the evolution of galaxies and how interactions between them shape that evolution. Their ability to provide information about the large-scale organization of matter within our universe and its potential pathways of formation is a part of what makes studying galaxy mergers interesting and important. They help us better understand the mysteries of the universe's evolution and allow us to make predictions about potential outcomes. Galaxy interactions are difficult to observe in real time. A typical merger may take 1 to 3 billion years, according to the Royal Astronomical Society. Astronomers use software to simulate the interaction and merger of galaxies in order to study how they change over time. The illustrious TNG simulation is a hydrodynamical simulation used to study cosmological evolution, which includes the large-scale formation and evolution of galactic structures. We use the data from the illustrious 3 run to produce plots of the changes in gas and stellar structures over the course of about 13 billion years. From a redshift of 10 to 0, there are 103 snapshots shown in the animation, and each snapshot refers to a specific redshift. Here, each green dot corresponds to a star, with higher density regions shown in yellow. They begin as a collection of gravitationally bound stars that undergo minor mergers to create a spiral galaxy. This galaxy continues to experience a few minor mergers before undergoing major merging and becoming a large elliptical, as seen in the last few snapshots. In this next animation, we are looking at the gas in the same system as it interacts and evolves over time. The green shows a collection of gas, with the dark blue regions representing more dense locations. As the galaxies form and merge, they can be visually identified by the blue dots that appear to swirl around each other and eventually collide. Galaxy merger simulations like this allow us to bridge between theory and observation. The images we gather from the night sky are only snapshots of millions of years of evolution, whereas simulations, like what we've gathered from Illustrious, are theoretical culminations of these snapshots. These models allow us to move through millions of years of data, where we may find results that correspond with actual observations. From this, we may extrapolate backwards in time to make predictions about the origins of these progenitor galaxies, and
ultimately, the origins of the universe.
And I'd say that that's pretty freaking cool.